Hey kids, Math here. We've got progress check number 7, our last project check, progress check from AP Classroom. We are done with those. So let's roll through this one. We've got KSP. This is kind of a standalone topic for us because it sits way up at the top of 16, chapter 16. But for the AP, this fits into equilibrium. So let's look at it. Could be some easy questions on it. We'd appreciate it if it was. They want us to write a mathematical explanation in our first one for the dissolution of PBI2. They want the mathematics behind this. So basically they're not looking for an equilibrium, a KSP expression. They're just looking for 7 point times 10 to the negative 9th is going to equal 4x cubed. Could be 4s cubed if you want to use it for solubility. Nothing real fancy there. That's the mathematical expression. In B, it says, hey, what happens if we throw this PBI2 into a pretty strong solution of NaI? This is common ion effect. And what common ion is they both PBI2 and NaI both share that iodine molecule. So the NaI being more soluble, that iodine is going to go into solution, take the place of the iodine in solution. So PBI2 cannot. So your answer is we would expect this to be less than the amount. PBI2 would be less due to common ion, comma, tell us what the common ion is, I minus, which suppresses dissociation. So C comes up and C says, hey, label the table showing KSP values and pick the one that has the greatest concentration. And so we've got to go through and find the biggest number. See, now the beauty of this, there's really not much calculation required because all three of these are twos. So it's PB to ion 2, PB to ion 2. And so the please report, explain. So PbCl2 would have the greatest because it has the largest KSP, resulting in the largest solubility of Pb2+. Pretty clean there. And those are the answers for those. Boom, boom, boom. Now let's look at 2. 2 is going to have us graph something, and it says equilibrium's established. We've got the HI equation. So now okay, so let me get to the graph part here. And it says the diagram's got to meet the following. So we want, I got to, pardon my split screen here. I got to be looking at the data on one thing and I got to be looking at the graph on the other. So the partial pressure of H2 is plotted at 0.30. Boom, there's H2. The I2 is going to be plotted at 0.15. And I'm pretty sure it wants these labeled. Okay, and HI is plotted at 50. So we'll make him green. HI is plotted there. Okay, and then in B, it says On the graph above, carefully draw the three curves for the three gases starting from the initial that we drew. The curves must show how the concentration of each of the three gases changes as equilibrium was established. And so the H2, if we've got 30 and 15 for the H2 and the I2, then those are both going to meet. The H2's going to level off at 20. The I2 is going to decrease. So the H2, level off at 20. The I2 is going to drop down. And the HI is going to increase and go up to 70. So I2 is our kind of our limiting here. All right, so that's what that should look like. And then we have on C, when the temperature in the vessel decreased, does the equilibrium shift right or left? This reaction is exothermic. We've got a negative delta H. Justify your answer. So exothermic, negative delta H. So what are we doing? We are decreasing the temperature. So removing heat will result in a shift to the right, or the other word we like is this would favor the products. Okay. Does the value of Kc increase? Does the value of Kc increase, decrease, or remain the same when the temperature is decreased? And so H2 and I2 are decreasing. So let's take a look at this. This is a really neat question, actually. So Kc is going to be equal to the HI squared over H2, I2. And so when the temperature is decreased, we're shifting it to the right. So we're increase the HI, which would decrease the H, decrease the I. And this is going to lead to a bigger Kc. So Kc increases. Okay, stick with me, almost there. In E, it gives us a nice little diagram. You guys have seen a lot of these diagrams. So let's see, in drawing the appropriate number of each type of molecule to represent the new equilibrium at a lower temperature, there's 1 H2, so we're going to have times 12. We're going to have one of those and one of those. So you'd have 12 HIs, you would have 1 H and 1 I to show that shift. I think that gets us to the very end of this problem. That's E. So there you go, little KSP, little shift. I like it. Fun kind of problem. Little equilibrium could show up. Kind of like it. I'm Smath. I do hope this video helped.